Dear students, now let us discuss about a new chapter, that is compact linear map. So the term compact is very familiar with you. Yes, it is compact, it is closed and totally bounded, or every open cover has finitely many subcovers. Here, let X and Y are any two non-linear spaces. Then if a linear map f from x to y is compact, if f of u closure, the closure of f of u means f of u closure is a compact subset of y. So where every u fall in x. F is said to be compact linear map. F is a linear map from x to y. Then f is said to be compact if for every u fall in x, f of u closure is a compact subset of y. Thank you. So also we know that we are familiar with the theorem. That is, if x is a compact space, then it is complete and totally bounded, as well as every sequence in x has a convergent subsequence. So now let us consider an important result. So the first theorem states that if x and y are non-linear spaces, f from x to y is linear, then f is compact. F is compact if and only if for every bounded sequence xn fall in x, then f of xn has a convergent subsequence in y. F of xn has a convergent subsequence in y. That's the theorem states that x and y are non-linear spaces. F is linear. Linearity of f is preserved. And the theorem states that this linear map f is compact when there exists a sequence xn fall in x with f of xn has a convergent subsequence in y. Reversely, when for any bounded sequence xn in x, f of xn has a convergent sequence in y, then that map f is compact linear strictly. It is compact. F is already a linear map. How to prove this one? First, suppose that f is compact. Then by the definition of the compact mapping, f is compact means for all u fall in x, f of u closure is a compact subset of y. Compact subset of, okay. And f is compact by definition for all u fall in x. What is u? U be an open map in x. Means u is defined as u equals set of all x fall in x with a norm x strictly less than 1. Then for any open body u fall in x, f of u closure is a compact subset of y. F of u closure is a compact subset of y. Okay. Now to show that for any bounded sequence xn in x, f of xn has a convergent subsequence. How to prove this one? Let xn be a bounded sequence in x. Xn is bounded in x. Xn is bounded in xn means for some alpha greater than 0, norm xn strictly less than alpha. Okay. Norm xn strictly less than alpha means norm xn by alpha strictly less than 1. Okay. Norm xn by alpha strictly less than 1 means xn, that implies xn by alpha falling where? That falling u. Why? U is constructed in this way. U is an open ball having radius 1. That is u equals set of all x fall in x such that norm x strictly less than 1. Here norm xn by alpha strictly less than 1. Clearly xn by alpha fall in u. Agreed. Then xn by alpha fall in u. Therefore f of xn by alpha. F of xn by alpha fall in f of u. Why? Because f is a linear. Agreed? F of. But what is f of u closure? Since f is compact, f of u closure is a compact subset of y. That means here f of u closure is compact. F of u closure is compact means f of u closure is complete and totally bounded. Moreover, we have a result if x is compact, that's a familiar result. If x is compact, then every subsequence or x has a convergent subsequence. According to that argument, f of u closure is compact, then f of u closure has a convergent subsequence. Has a convergent subsequence. Then therefore the subsequence, but f of xn by alpha fall in f of u. Therefore, every subsequence of f of xn by alpha converges in subsequence of f of xn by alpha converges in f of u closure. Okay, f of u closure, but f of u closure is a subset of y. Why? Because f is a compact map, then f of u closure is a compact subset of y. That means the subsequence of f of xn by alpha converges in where? Subsequence of f of xn by alpha converges in f of u closure, but it is a part of y, means f of xn by alpha converges in where? Y itself. Therefore, when f is compact, then f of xn has a convergent sequence in y. So this is the first part. Clear? Now, come to a reverse argument. What is the reverse argument? Next, suppose that for every bounded sequence xn in x, f of xn has a convergent subsequence in y, or convergent subsequence. F is compact. Now to show that f is compact, the reverse inclusion means first we assume that secant xn is bounded. Secant xn is bounded in x, and f of xn, secant f of xn has a convergent subsequence in y. Agreed. To show f is compact, it is enough to show that f of u closure is a compact subset of y. F of u closure is a compact subset of y. This is the requirement. 4. Let yn fall in secants yn fall in f of u closure. Secants yn fall in f of u closure. Then there exists, we can find a sequence xn fall in u. What is u? U equals set of all x fall in x with the norm x strictly less than 1. This is an open ball having a radius 1. Let xn be any, then let yn fall in f of u closure, then we can find a sequence xn in u such that norm yn minus f of xn strictly less than 1 by n, where n equals 1, 2, 3, etc. Norm yn minus f of xn strictly less than 1 by n. Since yn fall in f of u closure, agreed, since it is fall in f of u closure, there exists a sequence xn fall in u such that norm yn minus f of xn strictly less than 1 by n, where n equals 1, 2, 3, etc. Let xnj, sequence xnj be a subsequence of being a subsequence of x. Sequences. Sequence xnj being a subsequence of xn such that f of xnj converges to some y following y according to our hypothesis. Hypothesis states that for any bounded sequence xn in x, then f of xn converges to y. Since a sequence converges, subsequence also converges, then let xnj be a subsequence of xn such that f of xnj converges to y following y. Then, since f of xnj converges to y following y, then the subsequence ynj of yn, let ynj be a subsequence of yn such that this ynj also converges to some y following capital Y. Agree? According to these arguments. So, that means the subsequence in f of u closure, converges in where? Converges in y. Then according to our previous research, means when X is compact, it is complete and totally bounded, and every subsequence has a convergent subsequence. Therefore, that means from here, according to that argument, we have f of u closure is compact. F of u closure is a compact subset of y. F of u closure is a compact subset of y means, what is f of u? Then clearly f is a compact linear map by definition. Okay, so this is the reversing motion. Means for any bounded sequence xn is a bounded sequence. Let yn fall in f of u closure. We have to show that f of u closure is a compact subset of y. In order to prove f is compact, then according by the definition, f of u closure is a compact subset of y. That's our requirement. Let yn fall in f of u closure. F of u closure means we can find an xn fall in u with a norm yn minus f of xn less than 1 by u. So xnj be a sequence of xn such that f of xnj converges to y. Why? According to this hypothesis. Okay. Therefore, when f of xnj converges to y, norm yn minus f of xn less than 1 by n, clearly there exists a subsequence ynj of yn with a ynj converges to y. Means f of u closure is a compact subset of y. Then by definition, when f of u closure is a compact subset of y, where x and y are non-linear spaces, f from x to y be linear, by definition, f is a compact linear. So this is our first theorem in this chapter. Okay. Now, come to the second theorem. Next theorem states that if f is a compact map, f from x to y be a compact map. That's a compact map. Then f of u is totally bounded subset of y. Then f of u is a totally bounded subset of y. Totally bounded subset of y. Conversely, if y be a Banach space, f of u is totally bounded subset. F of u is totally bounded subset of y. F of u is a totally bounded subset of y. Then f is compact linear. Then f is compact. Listen, f from x to y is a compact map. F from x to y is a compact map means for any open ball u fall in x, f of u closure is a compact subset of y. Agreed? That's our definition. Then f of u is totally bounded. That's our first requirement. Reversely, f of u is a totally bounded subset of y. Then f is a compact linear map. That happens when y is, then if y is a Banach space, then f from x to y is a compact linear map. There is a restriction, y be a Banach space, not only a non-linear space. This should be happens only when y be a Banach space. That is the condition. Agree. How to prove this one? Proof is, come to the first part. F is a compact linear map. F is a compact linear map means, what is f of u closure? F of u closure is a compact subset of y. Agree. By definition of this compact linear map, f of u closure is a, since f is compact linear map, for every open set u fall in x, open set u fall in x, or open body u fall in x, f of u closure is a compact subset of y. Means f of u closure is compact. F of u closure is compact means this f of u closure is complete and totally bounded. F of u closure is complete and totally bounded. F of u closure is complete and totally bounded by the definition of compactness. compactness or by the condition of compactness. Then f of u closure is complete and totally bounded. Since f of u closure is complete, then clearly we have f of u is totally bounded. F of u is totally bounded. This is the first requirement. So first part is finished. Agreed. What about the reverse inclusion? Reversely, let y be a Banach space. Y be a Banach space. Means it is a complete non-linear space. The completeness is strictly preserved. Agreed. Y is complete. Then, and what is f? F of u is totally bounded. And f of u, for every open body u fall in X, f of u is totally bounded. F of u is a totally bounded subset of y. Totally bounded subset of y. F of u is totally bounded. Y is a Banach space. Listen, Y be a Banach space, complete non-linear space. F of u is a totally bounded subset of y. That means f of u is complete, or it is f of u closure is complete. F of u closure is complete and totally complete. Okay. F of u closure is complete and totally complete. Y be a Banach space. F of u is a totally bounded subset of y. So clearly f of u closure is complete and totally bounded. F of u closure is complete and totally bounded means yes, f of u closure is compact. That means f of u closure is compact. F of u closure is compact means f of u closure is compact means f is a compact linear. That is the requirement. Clear? So this is the second theorem. Agreed. The theorem, that's the proof is so simple. Now come to the next theorem. Next theorem states that if f is continuous, f from x to y is continuous. The x and y are non-linear spaces. F from x to y is continuous. And of finite rank, dimension of f is finite, or of finite rank, Then f is a compact member. Then f is compact. Then f is compact, and range of f is closed in. And R of f, range of f is closed in. So this is our first requirement. How to prove this one? F from x to y is a continuous member. The continuity is preserved, and also of f is finite rank. Finite rank means let f fall in BLX. F is a bounded linear map from x to y. Also f is continuous and is of finite rank. Since also range of f is yes, then f is compact and range of f is closed in y. So when f is of finite rank, clearly f is finite rank means what about a range of f? Range of f is finite dimension. Agreed by the definition of finite rank. Since f is finite rank, range of f is finite dimensional. Also, it is a closed subspace of y. Also, it is a closed subspace of y. So we have a theorem. When x be a normed space, the theorem says that x be a normed space, y be a subspace of x, y be a subspace of x. Let y is finite dimensional, y be finite dimensional, then y is complete and it is closed in x. Then y is complete and closed in x. So this is an important theorem in functional analysis. When x is a normed space, y is a subspace of x, and y is finite dimensional, then y is complete and closed in x. Here, let f1 and BLXY, since f and is of finite rank, clearly range of f is finite dimensional. Range of f is finite dimensional and subspace of y, then clearly range of f is closed subspace of y, according to this argument. Y is complete and closed in X. Clearly, range of f is closed. Range of f is closed in Y. Agreed, according to this thing. The range of f is closed subspace of Y means f of u closure is a, that means f of u closure is a closed subspace of or bounded subset of Y. It's a bounded subset of Y. What is f here? F is continuous. Since f is continuous, f is linear, f is bounded, and so it is f of u closure is a, it is closed, hence f of u closure is a bounded subset of Y. F of u closure is a bounded subset of Y means f is compact. Range of f is closed in Y, that's immediately from here. Since range of f is closed in Y, also f from X to Y is continuous. For any u fall in X, f of u fall in Y, then f of u closure is a bounded subset of Y. Why? Because its closeness property. Since f of u closure is bounded subset, clearly f of u is a compact linear. Agree. Then the converse of this, the above theorem. The converse of above theorem states that if X and Y are Banach spaces, if X and Y are Banach spaces, X and Y are Banach spaces, F is compact mapper. F is compact. F is compact, then and R of F is closed. R of F, range of F is closed in Y, then F is continuous and of finite range. There is a condition imposed. The reverse equation or the reverse statement of this theorem holds only when a condition imposed there, that is X and Y are Banach spaces. In previous case, only Y is a Banach space. In previous case, the reverse argument holds only when Y is a Banach space. Here the reverse inclusion of this theorem holds only when X and Y are Banach spaces. The condition, imposing condition is X and Y are Banach spaces. That is the crucial point. How to prove this one? So for, assume X and Y are Banach spaces. X and Y are Banach spaces. F is a compact linear map, and a range of F is closed in Y. These are the hypotheses. Then F is continuous. By X and Y are Banach, F is compact, range of F is closed. Then clearly this F is a continuous map. And range of F is a Banach space. Range of F is a Banach space. F from X to range of F is surjective. F from X to range of F is onto. Okay. Yes. So by open mapping theorem, what is open mapping theorem? By open mapping theorem, for any u fall in X, F of u is open.